of the right hand side. Because AI square, what's this? This is AI absolute value square plus some term I not equal to j AI AJ. Okay. Therefore, this is not less than AI square I from 1 to n. So our inequality is proved. So this inequality is proved. Okay. Now using this inequality, we can get the conclusion of our theorem. So to prove the theorem, if xk converges to A, then in the previous inequality, we take AI to be xki minus AI. We have xkj minus aj will not greater than I from 1 to n, xki minus ai square. Okay, what's this? This is exactly the distance between xk and a. But xk converges to a, therefore the right hand side converges to 0. So skj minus aj, the absolute value, also converges to 0. That is xkj converges to aj for every j from 1 to n. Okay, so this proves that if the sequence xk converges to a, then it converges to a component wise, because for every j, the corresponding component of xk converges to the component of a, conversion wise. So this is part of the theorem. This theorem is if and only if. Okay, we have proved only if part. Now the if part, this direction. If for any j from 1 to n, we have xkj converge to aj. Then, by the second inequality we just proved, we will have xk, the distance between xk to a, which is xki minus ai square. According to the inequality we just proved, this will not greater than the sum of the absolute value of xki minus ai. But for every j from 1 to n, the linear sequence xkj converges to aj as k goes to infinity. Therefore, every term in this sum goes to 0. Therefore, the right hand side is n linear sequence. Every one in this linear sequence goes to 0. Therefore, by the property of convergent linear sequence, we see that this goes to 0. Okay, thus sk minus a will goes to 0. That is sk converges to a. So we have proved that if xk converges to a component wise, then xk itself converges to a. Okay. So this theorem is very useful to get the property of convergent sequence in Rn. For example, we have this proposition. Okay, this proposition. If xk converges to A and yk is another sequence converges to another point B, and lambda and mu are real numbers, then the first conclusion is that lambda xk plus mu yk will converge to lambda A plus mu B. Okay, this is the first property. And the second property is that the scalar product of xk and yk. Here I use the dot notation to denote scalar product. Will converge to the scalar product of A and B. Or if you like, this is exactly this. This is the same. The first one is in dot notation. The other one is not in dot notation. Okay. How to prove this? For example, we prove the second conclusion. Okay. No. Suppose xk is xk1, xkn, and yk is yk1, ykn. Then, under the assumption of this proposition, for any I from 1 to n, xki will converge to ai, yki will converge to bi. Because xk and yk converge to ab respectively, therefore they converge component-wise. Hence, the scalar product of xk and yk, by definition, this is I from 1 to n, xki, yki. Now, xki converge to ai, yki converge to bi, so their multiplication will converge to ai, bi. Therefore, this in turn, every term converges to ai, bi, so this will converge to ai, bi. What's this? This is exactly the scalar product of a and b. So this property is proved. Okay. In a similar manner, you can prove the first property of scalar product. Of course, this proof use the component-wise conversion. In fact, we can also prove this result without using the component-wise conversion. For this purpose, we need to the following proposition. That is to say, if xk is converged to a in Rn, then the sequence xk is bounded. This is quite easy. Because xk converges to a, therefore the distance from xk to a converges to 0. Therefore, this real sequence, this distance consists of a sequence of real numbers. This is bounded. That is to say, there exists some r positive such that if the distance is less than r, so xk is xk minus a plus a. And using the triangle inequality, this will not greater than this, and this will be less than r plus a. That means our sequence xk is contained in this ball, centering on the origin and with radius r plus the norm of a. So xk is bounded. Okay. Now we have defined the convergence of a sequence in Rn. Xk is a sequence in Rn, then xk converges to a point A in Rn means the distance from xk to A. This is a sequence of a real number. So this sequence of real number goes to 0. So the convergence of a sequence in Rn is very simple. And we have proved that xk converges to A if and only if it converges to A component-wise for I1, 2 until n. And using this property, we have shown you that if xk converges to A, yk converges to B, then the scalar product of xk, yk converges to A dot B. Now I want to remind you that xk and yk are sequence in Rn, and but their scalar product is a sequence of real numbers. So this later convergence is a convergence of sequence of real numbers. Okay, different meaning. And we have used the component-wise convergence to prove this convergence. Now I will provide you another proof of the same result without using the component-wise convergence. How to prove this? The second proof. To prove that this sequence of real number converges to this number A dot B, we should estimate the absolute value of xk dot yk minus A dot B. We should estimate this absolute value. We applied a classical trick to add some point and subtract that point from the result. So this can be written as sk dot yk minus A dot yk plus A dot yk minus A dot B. Then we group the first two terms and the second two terms. So this is the absolute value of these two, of the sum of these two groups. And we apply the triangle inequality for real numbers because these two groups are all real numbers. So apply the triangle inequality, we get xk dot yk minus A dot yk plus A dot yk minus A dot B. And this can be written as xk minus A dot yk plus A dot yk minus B. Now this is the scalar product of 2 points in Rn. We can apply the Cauchy-Schwarz inequality. The first term will not greater than the norm of xk minus A multiplied the norm of yk. While the second term will be controlled by the norm of A multiplied the norm of yk minus B. So now xk converges to A and yk converges to B. Therefore, this term goes to 0. This term is also goes to 0. Can we deduce that this goes to 0? Can this be true? It depends on whether the norm of yk is bounded. If this is bounded by some r, then this is true.